Students, welcome to the next lecture of our subject. In the last lecture, we have learned the concept of what is dynamic impedance and derived the equation for dynamic impedance ZD is equals to L by RC. Similarly, learn the concept of resonant frequency, then learn the concept of parallel resonance in the parallel circuit. In today's lecture, we are going to see what are the properties of this dynamic impedance, then what is the relation between current and voltage, then what is the phase angle for parallel resonant circuit, and why parallel circuit is called as rejector circuit. See here the properties of dynamic impedance. So properties, these are the three properties. First one is the dynamic impedance ZD is a purely resistive because of resonance, voltage and current are in phase and the power factor is unity. As we know that during the resonance condition, voltage and current of parallel circuit are in phase. That means the phase angle phi is equals to 0 degree when circuit is at resonance, and power factor we are getting is unity because cos 0 is 1. Cos 0 is 1. Cos 0 1 आहे. व्होल्टेज आणि करंट रेझोनन्स कंडिशनला आपला इन फेज आहे. दोघांमधला फेज डिफरन्स फाय इज इक्वल्स टू 0 आहे. म्हणून तुमचं सर्किट रेझिस्टिव्ह आहे. रेझिस्टिव्ह म्हणजे काय? रेझोनन्स कंडिशन आली म्हणजे काय? रेझोनन्स कंडिशन अकर्ड मीन्स व्हॉट? XL is equals to XC is there. The condition is XL is equals to XC. XL is equals to XC. Hence the formula for impedance. Hence the formula for dynamic impedance ZD. Hence the formula for dynamic impedance ZD. L by RC is there. L by RC is there. So ZD is equals to R. That means the dynamic impedance is resistive in nature. Dynamic impedance is resistive in nature with power factor unity. With power factor unity. Similarly, next point. So this was the first point, first property. Second property is dynamic impedance represents the maximum value of impedance of the parallel circuit. See here, graph is shown to you. In the graph at the x-axis we have considered frequency in hertz, and on the y-axis dynamic impedance ZD is considered. Now see, at resonance condition, that is F is equals to FR, at F is equals to FR, our ZD is maximum. Maximum value of impedance is occurring at resonance condition and the nature is resistive. इथे बघा रेजिस्टर डायनामिक इम्पेडन्स ZD हा मॅक्सिमम मिळतोय मला या पॉइंटला. इथे मॅक्सिमम इम्पेडन्स मला मिळायला लागलेला आहे. ह्या पॉइंटला मॅक्सिमम इम्पेडन्स आहे ज्यावेळेस F इज इक्वल्स टू FR असेल आणि नेचर कसं डायनामिक इम्पेडन्सचं रेझिस्टिव्ह आहे. आणि इथं ग्राफ मध्ये आपण बघू शकतो बघा, फ्रिक्वेन्सी आणि डायनामिक इम्पेडन्स ZD यांचं रिलेशन आहे. यांचं ग्राफ प्लॉट केलेलं आहे आपण. त्याच्यात काय सांगू शकतो आपण? जर F इज इक्वल्स टू FR कंडिशन असेल तर माझा इम्पेडन्स हा रेझिस्टिव्ह आहे. फॉर F इज इक्वल्स टू FR इम्पेडन्स इज रेझिस्टिव्ह. इफ F इज लेस देन FR, फ्रिक्वेन्सी F ची व्हॅल्यू FR पेक्षा जर कमी असेल तर सर्किट माझं किंवा नेचर जे आहे ग्राफचं या ZD आणि फ्रिक्वेन्सीचं, डायनामिक इम्पेडन्स आणि फ्रिक्वेन्सीचे ग्राफचं इंडक्टिव्ह नेचर मिळतो मला. F इज लेस देन FR असेल म्हणजे रिझोनंट फ्रिक्वेन्सी पेक्षा नॉर्मल फ्रिक्वेन्सी व्हॅल्यूची जर व्हॅल्यू कमी असेल तर सर्किट माझं इंडक्टिव्ह नेचरला जातं रेझोनन्सच्या खाली येतं कंडिशनला असताना, आणि एफ इज ग्रेटर दॅन एफ आर जर असेल, म्हणजे नॉर्मल फ्रिक्वेन्सीची व्हॅल्यू रेझोनंट फ्रिक्वेन्सीपेक्षा जास्त असेल, इफ द condition is above resonance, f is greater than fr, then circuit is capacitive. So these are the properties, three properties for the dynamic impedances. These are the three properties for the dynamic impedances. Okay. So nextly we will see what is the relation of current and voltage with frequency. Current and voltage and frequency. Here we have learned the relation between frequency and impedance. Here we will see what is the relation between current of the parallel circuit with frequency. As like in series circuit, we are going to learn the concept of same concept, that is relation between frequency and impedance, frequency and current, frequency and phase angle in parallel circuit also. सिरीज मध्ये जशा प्रकारे इम्पेडन्स आणि फ्रिक्वेन्सी, करंट आणि फ्रिक्वेन्सीचं रिलेशन आपण बघितलं होतं, तसं पॅरलल मध्ये सुद्धा बघणार आहोत. सो सी हिअर नेक्स्ट हेडिंग इज द करंट अँड व्होल्टेज. पॅरलल रेझोनन्स म्हणजे काय? पॅरलल रेझोनन्स इज द कंडिशन ऑफ मॅक्सिमम इम्पेडन्स और मिनिमम ऍडमिटन्स. ऍडमिटन्स इज नथिंग बट रेसिप्रोकल ऑफ इम्पेडन्स. सो इफ इम्पेडन्स इज मॅक्सिमम, ऍडमिटन्स विल बी मिनिमम, and hence the source current I is minimum at resonant frequency. आपण डिराइव्ह केलेला आहे बघा डायनामिक इम्पेडन्स ZD च्या फॉर्म्युल्यामध्ये, की माझा जो काही सोर्स करंट I आहे तो मिनिमम कंडिशनला आहे, आणि त्याचा फॉर्म्युला मला मिळतो I is equals to V divided by RC. This is the formula. I is equals to V divided by L by RC or L by CR, where L by CR or L by RC is nothing but ZD. डायनामिक इम्पेडन्स आहे, L divided by CR म्हणजे डायनामिक इम्पेडन्स आहे, म्हणजे हा करंटचा फॉर्म्युला तुम्हाला मिळतो V by ZD, and the value of this current is minimum at a resonance condition. म्हणजे F is equals to FR ला ह्या करंटची व्हॅल्यू मला मिनिमम मिळते. हे बघा हा ग्राफ इथं दिसतोय बघा, या ठिकाणी F is equals to FR ही कंडिशन, इथे या कंडिशनला मला मिनिमम करंट व्हॅल्यू मिळते. करंटची व्हॅल्यू कशी आहे? मिनिमम आहे F is equals to FR ला. F is equals to FR ला ज्यावेळेस फ्रिक्वेन्सी F तुमची एक सर्टन व्हॅल्यूला असेल, हे बघा ही एखाद्या सर्टन व्हॅल्यूला, झिरोला बिलकुल नाही, झिरोला जर असेल तर मॅक्सिमम मिळते. चला ठीक आहे, झिरो कन्सिडर करू आपण. फ्रिक्वेन्सी झिरो असेल, करंट काहीतरी मला मिळणार आहे, करंटची व्हॅल्यू काहीतरी मॅक्सिमम पॉइंट मला इथे त्याचा मिळणार आहे. पण ज्यावेळेस F is equals to FR रेझोनंट फ्रिक्वेन्सी ज्यावेळेस येते, रेझोनंट फ्रिक्वेन्सीच्या केसमध्ये मला करंटची व्हॅल्यू मिनिमम मिळते, करंटची व्हॅल्यू मिनिमम मिळते. तर हा करंट अँड व्होल्टेजचा पार्ट आहे. तर बघा पॅरलल रेझोनन्स सर्किटला आपण इथे करंट रेझोनन्स सर्किट सुद्धा म्हणतो. का बरं? व्हाय वी ऑफन कॉल्ड दिस पॅरलल रेझोनन्स सर्किट ॲज अ करंट रेझोनन्स सर्किट? बिकॉज current circulating between the two branches is higher than, see, the current circulating between the two branches is many times higher than the source current, many times higher than the source current. हा source current आहे, मिनिमम आहे. तुम्ही जर मागच्या इक्वेशनला, मागच्या लेक्चरमध्ये इक्वेशन, इफ यू हॅव सीन दिस, व्हॉट रिगार्डिंग द IL अँड IC, रिगार्डिंग द IL अँड IC. So to get the value of IL is equals to I divided by cos phi L, I divided by cos phi L, or IC is equals to IL sin phi L. IL sin phi L. The two branch currents are having greater value than the source current I. Source current I पेक्षा तुमचा जो काही इंडिव्हिज्युअल ब्रँच करंट आहे मग तो सिरीज RL सर्किट मधला IL असेल आणि कॅपॅसिटरच्या अक्रॉसचा करंट IC असेल. व्हॉट एव्हर मे बी द व्हॅल्यू ऑफ द ब्रँच करंट ऑफ IL, व्हॉट एव्हर मे बी द व्हॅल्यू ऑफ IC, that value is greater than the source current I. That value is greater than source current I. And also we know in the case of resonance, source voltage V and source current I are in phase with each other. Are in phase with each other means both are having the phi of 0 degree. Both are having the phi of 0 degree. Hence, their equation for instantaneous voltage and current can be represented by these two equations. V is equals to Vm sin 2 pi FRT and I is equals to Im sin 2 pi FRT. So these are the equations for voltage and current, instantaneous voltage and current of the parallel resonant circuit. Now if we see the relation, both are in phase. For example, see here, I will draw a voltage waveform here. One minute, I will. Now see, if this is our voltage waveform, and this point is maximum point, Vm. So the equation of current will be, or the waveform for the current will be same, that is starting from the 0 point. Only the difference is the maximum point for the current is somewhat reduced. Maximum point for the current is somewhat reduced. So this is the voltage waveform and the next one will be the current waveform. See here, the maximum point is here Vm. This is the maximum point Vm, and this is the maximum point Im for the current waveform. Im and Vm. See, the magnitude of Im is less than Vm. Why magnitude of Im is less than Vm? See, due to this formula, Im is minimum. The source current I is minimum at resonance condition. So my Im minimum current will be given by this formula, Vm divided by Zd. So the magnitude of Im and Vm, if we compare it, the magnitude of Im is less than magnitude of Vm, but both are in phase, both are starting from same point, both are starting from 0 point. So this is the waveform for current and voltage in the case of resonant circuit. Next is the phase angle of parallel resonant circuit. See the graph in the left hand side. The graph represents on the x-axis value of frequency, on the y-axis value of phase angle phi. Value of phase angle phi. See, parallel resonant circuit is inductive in nature before resonant frequency. We have learned this concept. For F less than Fr, circuit is inductive in nature. Circuit is inductive, and for F greater than Fr, circuit is capacitive. Circuit is capacitive. Now for F less than Fr, that is when the circuit is inductive, when the circuit is below the resonant frequency, see the value of phase angle starts from minus 90 and ends up at 0 degree. Ends up at 0 degree. When our frequency starts from 0 and reaches to Fr, means in the range of frequency 0 to Fr, for this frequency my circuit will be inductive, and hence phase angle between the voltage and current is given in the form of minus 90 to 0 degree. Phase angle will be minus 90 degree to 0 degree as shown in the graph. See this part here. So this part, this is the inductive nature. This is the inductive nature. Now when F is equals to Fr, circuit is purely resistive. See, at Fr it reaches to 0, phase angle is 0, and for the frequencies above F, above Fr, resonant frequency पेक्षा वरती जर frequency असेल, then the circuit is capacitive. See the graph for this capacitive. This is the graph for our capacitive circuit. Graph for capacitive circuit. See here now, positive value is achieved for capacitive and negative value is achieved for inductive circuit, and this condition is for F greater than Fr. This condition is for F greater than Fr, and this inductive condition is for frequency in the range of 0 to Fr. 0 to Fr. And at this point phase angle is 0 because this is F is equals to Fr. F is equals to Fr. So this is the phase angle of parallel resonant circuit. Now the main question arises here is that why parallel circuit is called as rejector circuit. Now next point we are going to learn is the why parallel circuit is called as rejector circuit. See here, series circuit is called as acceptor circuit, and why parallel circuit is called rejector circuit. When you will understand that parallel circuit is rejector circuit, automatically you will understand that series circuit is called as acceptor circuit. जसं तुम्हाला इथे पॅरलल सर्किट रिजेक्टर सर्किट का बरं म्हणतो आपण हे लक्षात येईल, तसंच तुम्हाला लक्षात येईल याच्यातूनच की आपण सिरीज सर्किटला एक्सेप्टर सर्किट का बरं म्हणतो. नाउ these are the points why we call the parallel circuit as a rejector circuit. There may be a question for 2 marks in your question that why parallel circuit is called a rejector circuit. Now at resonance condition, see, we have learnt at resonance that parallel circuit has maximum impedance. Parallel circuit has maximum impedance. But in the case of series circuit, the impedance is minimum. Impedance series circuit la minimum asto. This means that the behavior of this parallel circuit is exactly opposite to the series circuit. Series circuit at resonance. Also, if parallel circuit is connected in series with an AC source, it offers infinite impedance. At F is equals to Fr, and will not allow signal of this frequency to pass through the output. काय करतो, पॅरलल सर्किट जर मी सिरीज मध्ये कनेक्ट करायचं ठरवलं, एसी सोर्स लावून सिरीज मध्ये कनेक्शन जर करायचं ठरवलं पॅरलल सर्किटचं, दोन पॅरलल सर्किट मी सिरीज मध्ये लावले, तर प्रॉब्लेम काय होतो, F इज इक्वल्स टू Fr ला इन्फिनाइट इम्पेडन्स. इम्पेडन्स मीन्स व्हॉट? इम्पेडन्स मीन्स अपोजिशन क्रिएटेड ड्यू टू रेजिस्टन्स अँड रिएक्टन्स. R आणि X मुळे क्रिएट झालेला अपोजिशन इज कॉल्ड एज इम्पेडन्स. And at F is equals to Fr, at this condition, this series combination of parallel circuit gives infinite impedance, create infinite opposition. So the frequency of value, resonant frequency, the frequency whose value is equal to the resonant frequency, are not allowed to pass through the circuit, pass through the output. F is equals to Fr व्हॅल्यू असलेल्या सिग्नलला पास व्हायला अलाउच करत नाही, तो रिजेक्ट करतो. रेझोनन्स कंडिशन मध्ये तो रेझोनंट फ्रिक्वेन्सीला रिजेक्ट करायला लागला. रेझोनंट फ्रिक्वेन्सीला सोडतच नाहीये, तो रेझोनंट पेक्षा कमीला सोडेल, रेझोनंट पेक्षा जास्तला सोडेल, पण रेझोनंट कंडिशनला ज्या फ्रिक्वेन्सी येते त्यावेळेस तो नाहीच म्हणतो, मी अलाउच करत नाही. आय विल नॉट अलाउ दी resonant frequency to pass through my output, to pass through my circuit. Either I will allow the inductive circuit, either I will allow the frequency less than resonant frequency or frequency greater than resonant frequency, but I will not allow the frequency equal to resonant frequency. So that's why parallel circuit is called as rejector circuit. Parallel circuit is called as rejector circuit. Why it is called rejector? Because it rejects the frequency equal to resonant frequency. F is equals to Fr is rejected in this circuit. या सर्किट मध्ये F is equals to Fr ची कंडिशन तो रिजेक्ट करायला लागतो. But when two parallel circuits are connected in series, the condition is most important. If two parallel circuits are connected in series, then and then only the circuit rejects the resonant frequency, and that's why parallel circuit is called as rejector circuit. That's why parallel circuit is called as rejector circuit. Okay? Now the next point is the Q factor. Q factor. We have discussed this Q factor initially also. Q factor is nothing but the efficiency of a inductor and capacitor in the circuit to store the energy, to store the charge. Q factor म्हणजे एखाद्या इंडक्टर आणि कॅपॅसिटरचं एनर्जी स्टोअर करण्याची इफिशियन्सी, एनर्जी स्टोअर करण्याची कॅपॅसिटी, त्याला आपण Q फॅक्टर म्हणतो. दॅट इज कॉल्ड Q फॅक्टर. In the case of series circuit, we can define the Q factor as the voltage magnification provided at resonance. Series circuit च्या केस मध्ये मी त्याला डिफाइन करत होतो voltage magnification at resonance. Resonance ला क्रिएट होणारा voltage magnification. But in the case of parallel circuit, I will define this circuit as current magnification provided at resonance. Current magnification provided at resonance. So this is the definition of Q factor for parallel circuit. Q factor or quality factor for the parallel circuit. See here, initially also we have discussed that even though the resultant current I is minimum, at resonance branch currents IC and IL are very large. Branch currents IC and IL are very large. For this you can refer the phasor diagram of parallel circuit. For this you can refer the phasor diagram of parallel circuit. See this one. If you take the projection on here, the value of I will be less than IL and IC. Value of I is less than IL and IC at resonance condition. At resonance condition. And therefore this circuit is also called as current resonance circuit. Initially we have discussed current resonance circuit. Why we call this circuit as current resonance circuit? See, in this we have discussed the parallel resonance is also called as current resonance circuit because current circulating between the two branches is many times higher than source current. That's why this circuit is also called as current resonance circuit. Okay, so this is the expression for a Q factor. Now we have defined this Q factor for parallel circuit as Q factor is nothing but the current magnification provided at resonance. So current magnification will be given by current through inductive branch divided by resultant current. Current through inductive branch divided by resultant current, that is IL divided by I. But we know the value of IL is V by ZL, and ZL is given by under root of R square plus omega square L square. So the formula for IL becomes V divided by under root of R square plus omega square L square. But we know that R square plus omega square L square is nothing but L by C. All this we have derived in the initial lecture. पहिल्या लेक्चर मध्ये आपण हे सगळं डिराइव्ह केलेलं आहे. So you can refer that lecture how this value has been occurred in this equation. So R square plus omega square L square is equals to L by C. So replace the value of R square plus omega square L square by LC. The value of IL we are getting here. Therefore the value of IL I am getting here is V divided by under root of L by C. V divided by under root of L by C. So this is the value of IL. So put the value of this IL in this equation. Put the value of IL in this equation, and the value of I is V divided by L by RC or L by CR. This we have derived from the formula for dynamic impedance. So put this value of IL and I in this equation. So Q becomes IL is V divided by under root of LC. I will write here the formula. V divided by under root of L by C divided by the value of Li is V divided by L by CR. So the value of IL is V divided by under root of L by C divided by V divided by L by CR. So this will be the Q Upper one is IL, this one is called as IL and this is called I. But I can write this equation in this format. Q is equals to V divided by under root L by C into the denominator part of L by CR goes to numerator and the numerator part for the V is in the denominator. Mathematical arrangement. So VV get cancelled. So L by CR, I can write this here also, V into CR. इथे पण मी तो C लिहू शकतो. Okay, so you will get the quality factor Q as 1 by R under root of L by C. 1 by R under root of L by C. So this is the formula for Q factor. Now remember the formula for Q factor of series resonant circuit. We are getting the similar formula as Q is equals to 1 by R under root of L by C. So this is the formula for Q factor. Now next is the effect of this Q on bandwidth. Bandwidth वरती या क्वालिटी फॅक्टर Q चा काय इफेक्ट होतो हे आपण आता बघणार आहोत. Now what is bandwidth? We have defined this definition of bandwidth. We have learned the concept of bandwidth in the case of series resonant circuit. What is the definition? What is the formula? We have learned the concept of bandwidth in the series resonant circuit. The definition will be same for the parallel resonant circuit. Okay. Just the concept of effect of Q and bandwidth will be different for this parallel circuit. Now see, this is the graph for effect of quality factor on bandwidth. When a large number of quality factor is there, our bandwidth becomes small here. But the graph is starting from maximum value and at FR it is reaching to minimum value and again from FR it is going to the maximum value. But in the case of series resonant circuit, if you remember the graph of series resonant circuit, then you can understand that the graph is starting from minimum value when the condition is less than FR. When F reaches at point FR, when the resonant frequency is occurring, when the resonance condition is occurring, the value of that graph was maximum and again at frequency greater than FR, value was reducing. But in the case of parallel circuit, at condition F less than FR, maximum value is coming, at F is equals to FR, minimum value is reaching and again it is coming to the maximum value. म्हणजे पहिला ग्राफ जर मी बघितला, हा this is the graph for parallel resonant condition. But if I draw the graph for the series resonant condition with the same value on X and Y axis, the graph will occur in this format. This is the graph for series resonant circuit. This is series resonant circuit graph. Relation between Q and bandwidth. And in the when the small q is there, quality factor is small, then our bandwidth will be large. So this is the graph for parallel resonant circuit. And if we draw this graph with the same quantity for small q and large bandwidth, the graph is nearly like this. The graph is nearly like this. See here, for series resonant circuit at F is equals to FR, I am getting the maximum point here and here. but in the case of parallel circuit I am getting the minimum point here. I am getting the minimum point, means whatever we are going, whatever conditions, whatever terms we have learnt in the series circuit are either opposite to the series circuit in parallel circuit. सिरीज मध्ये जे काही आपण कन्सेप्ट शिकलो होतो, जे काही ग्राफ शिकलो होतो, जे काही व्हॅल्यू आपण शिकलो होतो, त्याच्यापेक्षा अपोजिट आपल्याला पॅरलल सर्किट मध्ये सापडतं. म्हणून सिरीज सर्किट इज कॉल्ड एज एक्सेप्टर सर्किट अँड पॅरलल सर्किट इज कॉल्ड एज रिजेक्टर सर्किट. सो दिस इज द व्हॅल्यू ऑफ बँडविड्थ ऑन this is the effect of quality factor on bandwidth. Quality factor on bandwidth. Now the last point here we are seeing is the magnification in parallel resonant circuit. We have learned the concept of magnification in series resonant circuit, and we have concluded that the voltage magnification is taking place in the series resonant circuit. Here current will be magnified. Here current will be magnified. How the current magnification is taking place? So we will consider the current through inductor and current through capacitor, because resonance is occurring when inductor and capacitor is present in the circuit. When inductor and capacitor is present in the circuit. So in the case of series resonant, we were finding the voltage across inductance and capacitance, but in the case of parallel resonant circuit, here we are going to find out current through inductor and capacitor. सिरीज रेझोनंट मध्ये आपण व्होल्टेज मॅग्निफिकेशन काढत होतो, तिथे आपण इंडक्टरच्या अक्रॉसचा व्होल्टेज बघत होतो. इथे आपण पॅरलल रेझोनंट मध्ये इंडक्टर आणि कॅपॅसिटरच्या अक्रॉसचा करंट फाइंड आउट करणार आहोत, कारण इथे आपल्याला करंट मॅग्निफिकेशन फाइंड आउट करायचंय. करंट मॅग्निफिकेशन फाइंड आउट करायचंय. सो राईट हँड साइडला तुम्हाला फिगर दिसतीये करंट थ्रू आयएल साठी. ओके, सॉरी, करंट थ्रू पॅरलल रेझोनंट सर्किट आपल्याला फाइंड आउट करायचं आहे. सो करंट थ्रू इंडक्टर्स वी आर गोइंग टू फाइंड आउट. करंट थ्रू इंडक्टन्स. Current through inductance we are going to find out here. At the right hand side you can see the parallel resonant circuit having the supply voltage V and frequency of f hertz and frequency of f hertz. Now see here again the voltage across inductor here written. Actually this should be current across. This should be current across inductor, not voltage across. Current across inductor. So these are the silly mistakes in the TechMax book. So that's why I am telling you to refer the standard reference books. Then the current across the inductor is given by, current across the inductor is given by IL is equals to V by ZL. By this formula, inductor current or the branch across the inductive branch is IL. Current across inductive branch IL is given by this formula, but replace R square omega square L square by this L by C and IL by V under root of L by C. After solving this equation, see, I is common, L by RC and divided by under root of L by C. After solving this equation, we can see that this is the arrangement. He arrangement kashi ali, how this arrangement is occurring? See, L by RC divided by under root of L by C divided by under root of L by C. So 1 by R into L by C divided by under root of L by C. under root of L by C. Now we can write this L by C as multiplication of under root of L by C multiplication of under root of L by C, that is L by root of L by C into root of L by C is L by C, and divided by root of L by C. So this root of L by C and this root of L by C get cancelled. So what is remaining here? 1 by R under root of L by C. And right now only we have seen the this formula 1 by R under root of L by C is given or is called as quality factor Q. As called as quality factor Q. And therefore the current is the magnification formula for inductor current IL is this Q into I. Q into I. That means the current across the inductive branch is magnified Q times the source current. Q times the source current. See here our point that at a resonance condition source current is minimum than the branch current. That point is getting proved here. जे आपण कंडिशन बघितली होती की रेझोनन्स कंडिशनला सोर्स करंट आय हा ब्रांच करंट पेक्षा कमी असतो. इथे मला कळतंय बघा, इथे मला ती व्हॅल्यू डिफाईन होतीये. सोर्स करंटच्या क्यू टाइम्स जर मी व्हॅल्यू घेतली तर मला इंडक्टिव्ह ब्रँचचा ह्या आर आणि एल हा जो इंडक्टिव्ह ब्रँच आहे या इंडक्टिव्ह ब्रँचचा करंट मला क्यू टाइम्स मिळतोय सोर्स करंटच्या या इंडक्टिव्ह ब्रँचचा. म्हणजे इथे ब्रांच करंट माझा सोर्स करंट पेक्षा जास्त आला. सिमिलरली फॉर कॅपॅसिटन्स ऑल्सो वी कॅन डिराइव इट. दीज आर द कन्क्लुजन्स फ्रॉम दिस इक्वेशन, फ्रॉम दिस डिराइव्ड दॅट द एक्सप्रेशन इज शोइंग दॅट द current through inductive branch or current through inductor IL is Q times the source current. If Q is greater than 1, IL is greater than 1. म्हणजे क्वालिटी फॅक्टर जर 1 पेक्षा जास्त असेल तर ऑफकोर्स तुमचा करंट थ्रू इंडक्टर सुद्धा वाढणार आहे. म्हणजे परत बघा मॅग्निफाय झाला करंट तुमचा. इथे करंट इज मॅग्निफाईड इन दिस केस. इट इज सेड दॅट करंट इज मॅग्निफाईड इन पॅरलल रेझोनंट सर्किट. Similarly for capacitor, same derivation will be there. See the derivation here. IC is equals to V by ZC or V by XC. IC is equals to the formula for 1 by XC is, actually XC is 1 upon 2 pi FC. So 1 by XC is equals to 2 pi FC, but F is equals to FR in the resonant circuit. So formula becomes V into 2 pi FRC. But we know the formula for FR is 1 upon 2 pi under root LC. 1 upon 2 pi under root LC. And voltage is given as current into dynamic impedance. Remember the formula for dynamic impedance ZD. And the value of ZD is L by RC. Putting this value in the value of IC, we are getting this derivation. See the derivation. So again here in this stage, similarly it becomes L by C I can write that root of L by C into root of L by C multiplied by root of C by L. Root of C by L. So this will cancel each other, and what is remaining? Root of L by C and 1 by R. And again we can say this is the quality factor Q. So this is the formula for current through capacitor. See, current through capacitive branch IC is also magnified Q times the source current. Q times the source current. So this is also the conclusion. Same conclusion will be occurring for the capacitor current IC also. Now from this, here we have understood that whatever assumption we have made in the parallel resonant circuit regarding the supply current, that the supply current is minimum and branch currents are having the large value, that point has proved in this magnification factor. मॅग्निफिकेशन फॅक्टरच्या पॉइंट मध्ये आपण ते प्रूफ केलेलं आहे. ओके, सो दीज आर द कॅरेक्टरिस्टिक्स. इम्पेडन्स इज ZD is equals to L by CR. ZD is purely resistive at F is equals to FR, and resonant frequency is formula this one. Current magnification and IL is equals to IC is equals to Q into I. V in I are in phase. BW is inversely proportional to Q. This is the characteristics of parallel resonant circuit, and this is the comparison for the series and parallel circuit. You stop your video and you yourself compare this series and parallel circuit, so we'll understand what is the difference between series circuit and parallel circuit, and why parallel circuit is called rejector circuit and why series circuit is called acceptor circuit. You can understand from this कंपॅरिझन. या कंपॅरिझन मधून तुम्ही इथे बघू शकताय. इथे तुम्ही तुमचा व्हिडिओ स्टॉप करून हे कंपॅरिझन बघू शकताय. ओके, सो वी विल स्टॉप हियर. थँक यू. In the next lecture we will see the numerical part for parallel resonance circuit.